Hi, it's WaveTheory, and I mentioned in my launch video of this channel where I review sound gear that I wanted to do some teaching videos and talk about some of the basic science behind audio reproduction and whatnot. So we're going to jump into that today by talking about output impedance and damping factor. Now, I have been reviewing sound gear for a little over a year now with written reviews on HeadFi and Hi-Fi Guides forum, and I put a link to my review library in the description below. And if you want to support me in this channel going forward, please like, subscribe, and ring the bell. All right. So if you've looked into buying a headphone amp in particular, but it's true of speaker amplifiers as well, if you've looked into buying one lately, you've probably seen a spec out there that is this thing called output impedance. And you've probably seen in different places around the web that less output impedance is usually considered better. Okay, lower the better on that. And then you've probably also heard of this thing called damping factor, which involves the output impedance, but also gives you some kind of a relationship between the interaction of the amplifier and the speaker or headphone driver. Okay, in both cases. Works for speaker amps and speakers and headphone amps and headphones. What are these things and what effects do they have on sound? We want to talk a little bit about that today. All right, some basics about circuit stuff and electricity. Now, I am going to just put a broad caveat in here to the experienced physicists and engineers out here. You are not my target audience, okay? I'm going to frame things in terms of energy here, which is a little bit different, and I'm going to avoid terminology like voltage drops and Kirchhoff's rules and phasor diagrams and like all of that kind of stuff, which I know exist and are important, but this video is targeted more towards inexperienced audiophiles and more of the lay audience who hear these terms being floated around out there but don't really know what they mean. I want to explain just enough and in just a basic enough way that they can make sense of why these numbers are important and how they affect the sound. All right, so here's a confession from a scientist about our understanding of the natural world, and that's that we don't really know what electric charge is. Okay, we know that electric charge exists, but we don't really know what it is. We do know, however, that it appears to be some form of energy. And we also know of ways that we can move that charge or that electrical energy around and get it to do things. Now, in my intro video, if you watch that where I introduced myself, I talked about being a physics professor. I am a physics professor. And so I am going to give you a free lesson here in the punchline of like college physics 2 or university physics 2, at least the electromagnetism portion, which makes up the bulk of the course. And that is electric charge is a type of energy. And then the course spends a lot of time talking about the basics of how we can move that energy to places we want it to be, to do things that we want it to do. All right, so keep that idea in mind as we move forward in this video talking about output impedance and damping factor. All right, now audio circuits use alternating current. And what that means is just that the direction of electrical energy flow changes from backward and forward, all right, as time goes on. And so what happens is that an audio signal, okay, something or an electrical signal that models a sound wave essentially looks like a wave, okay? This is technically a cosine wave here, but it's modeled as a sinusoidal kind of wave. And what we do with an audio circuit is we take that wave and then we take some source of added energy, which typically comes from the electrical energy that your power plant is creating and then delivering to your house, and you plug into the wall to access it. And your amplifier, your audio amplifier, is taking that signal and that electrical energy from your power plant and combining them together to increase the amplitude, amplifier amplitude, pretty clever how they did that, right? Okay, to increase the amplitude of that electrical signal, which is modeling a sound wave. And then it delivers that higher amplitude electrical signal to a speaker or headphone driver, which then vibrates back and forth in air and creates a pressure wave that travels to your ear, and you hear that as sound, okay? Now, over here, all of this stuff from the incoming electrical signal combined with the power from your power plant to create a higher amplitude signal, that is all electrical energy happening in the electrical energy domain. And then what the headphone or speaker driver does at the other end is take that electrical energy and convert it into mechanical energy, specifically the mechanical energy of the motion of that driver vibrating back and forth. Okay, now resistance, electrical resistance is kind of basically really just what it sounds like. Okay, it makes it more difficult to move electrical energy around. All right, and now you've probably seen resistors that look like this, just little electrical components that go into electrical circuits that we intentionally put in there to control and reduce the amount of electrical energy that's flowing around in the circuit. However, anything that you plug in, like televisions or a hairdryer or a light bulb or a toaster, okay, anything that you plug in is looked at, or the electrical circuit sees as a resistive load. Okay, and that reduces the amount of energy that can flow through the circuit because it is a load on the amplifier or your power source. Okay, but there is another way to think about resistors. And that is that resistors are devices that we put into circuits to convert electrical energy into some other form of energy. All right, a classic example is just a battery and a light bulb. The battery produces electrical energy. That electrical energy goes to the light bulb, and then that light bulb converts the electrical energy into light energy and often thermal energy, which we feel as heat. You've probably touched it, particularly an incandescent light bulb at some point in your life and said, ow, that's hot, okay? Thermal energy, all that is taking some of the electrical energy that came from the battery or whatever your power source is and converted it into other forms of energy like light and thermal energy, which we feel is heat. Now, in an audio circuit, oops, I'm getting ahead of myself here. Now, we can model these real-world circuits with simpler circuit diagrams where these parallel bars here of uneven length represent a DC power source like a battery, and then this symbol right here stands in for a light bulb. Now, more generally, you have your source here, and then we use these diagonal squiggly zigzags right here to represent any kind of a resistor on a circuit. Okay, now in audio, in an audio circuit, we're going to replace the light bulb with a speaker or headphone driver, and we're going to replace the power source with an amplifier. Okay, and now that changes the circuit diagrams a little bit. Okay, I'm not going to use an actual symbol for a headphone. I don't think there is a universal symbol for a headphone or speaker driver. So I'm just going to use this picture of my Lawton modded TH900s because those Lawton cups are beautiful. Okay, let that stand in the circuit diagram for our load, and then we'll use the accepted symbol for AC circuit generator or an AC power source, which is going to represent our amplifier here with this circle with a sine wave in it. Now, it's important to remember then that a speaker or a headphone driver converts electrical energy into mechanical energy. Sorry about this little typo here. So into mechanical energy. Okay, now I think we're ready to talk about output impedance, because the output impedance is defined as the load at the speaker or headphone output of an amplifier due to the amplifier's construction. And it's an internal thing. It's an internal load. So however the amplifier is constructed, there is a non-zero impedance that occurs at the output. Okay, so here is a picture of a Schiit Asgard 3. Here's the headphone output right here. The output impedance is very much like having one of those resistors that we saw a moment ago placed right there at the output. Okay, now sometimes this is done on purpose. Like for example, before we had this massive proliferation that we've had of desktop headphone amplifiers over the past couple of decades or so, headphones in particular were like plugged into the headphone outputs on a receiver or a speaker amplifier. And now a speaker amp has a lot more power than most headphones need. And so if you were to just plug directly into a headphone amp or into your headphones directly into a speaker amp, you'd probably blow your head up. Just way too much power going through there. So they put a resistor in front of the headphone output to drive up the output impedance and thus reduce the amount of energy that was going to the headphone. And so that increased the output impedance, and that's where, at least with headphones, we started to need to worry about this thing called impedance matching, where you're worried about output impedance and the impedance of your headphones and that sort of thing. Okay, so then modeling that here, we have our amplifier, we have our speaker, and then in series with those two things, we have our output impedance, which we'll use that squiggly right there to represent. So what's happening? Well, remember that resistors convert electrical energy into some other form. So we have our circuit here. The law of conservation of energy tells us that energy is neither created nor destroyed, which means that the energy that comes from the amplifier doesn't just go away, it has to go somewhere. All right, and that amplifier generates a finite value of energy. So if we freeze time, we pause time at any given instant, you have some music playing. The amplifier has a set amount of energy that it can deliver to the circuit right then. Okay, and then all of the resistors are the loads in the circuit, which means the output impedance, the speaker driver, anything like that, converts that energy that's available to another type, which also means that the sum of the energies that each load converts, okay, some amount of energy here that's converted, some amount of energy here that's converted, those two amounts must sum to the amount of energy that came from the amplifier. And this is where I'll make a special note to the physicists and engineers out here that, yes, I realize that these energy differences are voltage drops, and I'm talking about Kirchhoff's loop rule here. And that voltage, remember, is defined as the electric potential energy per unit charge, or at least the difference in the electric potential energy per unit charge across a resistor. And that's where I'm coming up with this energy conversion and dissipation idea here. Okay. Now, the larger the output impedance then, because we have a sum here, energy converted to something else here, plus energy converted to something else here, is equal to the total energy coming out of here. That means the larger this output impedance, the less energy now is available to go to the headphone or speaker driver to convert to mechanical motion. All right, so now let's talk about damping factor. So impedance, just to be clear, if this was not said earlier, impedance is to AC circuits what resistance is to DC circuits. Okay, so it's just a load on the circuit. The damping factor, the fancy definition, if you will, is the ratio of load impedance to source impedance, which basically just means take your driver impedance, which is typically like 4 or 8 ohms for a speaker, and then for headphones it varies wildly from like 25 ohms on up to 600 ohms. Okay, but you take your load impedance, your driver impedance, put it on top of your fraction, and then you sum the output impedance and the wire resistance, put that in the denominator. Now, wire resistance tends to not have a huge effect because a well-made wire will have very, very low resistance. So it's essentially the ratio of driver impedance to output impedance, right? And that's your damping factor. Now, most manufacturers are going for a damping factor of 8 or more, meaning the driver impedance is at least 8 times the output impedance. Now, physically, what this means is that it's a measure of driver control, specifically the ability of the amplifier has to stop the driver's motion once it has already started moving. Okay, damping. You put a damper on something, you slow it down, or you resist it somehow, right? You control it more and you lessen the effect of whatever is happening. That's what it means to damp something. So damping factor is talking about stopping the driver's motion. All right, and then higher damping factor just means more driver control. Okay, so again, back to this energy framing. Said this already a little bit, but just to go through it again here, both the output impedance of the driver and the drivers will convert some of the electrical energy into another form. All right, and then the output impedance and the driver must share the available energy from the amplifier at any given moment in time. And then that means that the more electrical energy the output impedance converts to some other form, and usually the output impedance is going to convert that to thermal energy, which we will feel as heat, then the less available energy there is for the driver to convert the electrical energy to mechanical energy. And thus, you have less driver control. Then the question becomes, can you hear this? Can you hear this effect? And the answer is absolutely yes, you can in certain situations. Let's take a quick look at why. All right, I took this graph here. This is the impedance curve for the Sennheiser HD650 as measured by interfidelity a long time ago. And so this magenta curve right here gives you an idea of the amount of impedance that the HD650 has at the frequencies that we see down here. And I want to draw your attention to a couple of things. One, this impedance is not constant throughout the audible frequency range. We have this spike here that is centered somewhere between 80 and 90 hertz, and then we have this slow climb upward as frequency goes up in the treble range. Now, why is this spike here? Has to do with the resonant frequency of the driver, which is just where the driver's motion gets really hard to control. Okay, and why that is for another video. And then why does this impedance climb up here? That's because the voice coil of a dynamic driver is an inductor, and inductors become a harder load with higher frequency. Okay, now this peak right here, we will have high damping factor here, and we will have high damping factor here. And this is also where we need lots of amp energy to control driver motion. All right, and that's important because, again, it is a zero-sum game here at any given instant in time between the energy the output impedance takes out and transfers to thermal energy versus the energy available for the driver to convert to mechanical energy. And then we also have a variable damping factor here. High damping factor here and here because the load impedance is high. Low damping factor here in the really deep sub-bass, and then throughout this region here where the load impedance is relatively low. Okay, and so this means then that we have some areas within the audio spectrum that where we have high driver control, high driver control, high driver control, and we have other areas where we have low driver control. All right, what does this mean here? So if you look down here, in these bass frequency regions here, well below about 80-ish hertz, as this graph shows, okay, we're going to have a low damping factor, which means low driver control, which means we can often have boomy, bloated, sloppy bass. Just really muddy, uncontrolled. Okay, think like, those subs that you put in the back of a car that all you care is just boom and sheer output, like that kind of a sound almost down here. And then it gets less controlled in this region too. All right, and so what you might perceive here with these low damping factors is like an increase in bass presence, but it's going to be muddy, sloppy, and just not very good pitch definition and that sort of thing. Okay, and then an important point here is that high impedance headphones avoid this problem. Okay, what they have done with high impedance headphones is they've pushed the overall impedance so high that the damping factor is like always 8 or more if you're plugging into a high output impedance device like a speaker amp that has a headphone tap on it, or like an output transformerless tube amp that has a very high output impedance. So Sennheiser, Beyerdynamics, some AKGs, some Audio-Technicas, have 250, 300, 600 ohm impedances so that we have a high damping factor across the board if we have high output or high output impedance. Now, many dynamic driver headphones anymore do not have high impedance. They're like 25 ohms, 32 ohms, occasionally 50, but usually almost always now they are below 50 ohms. So if you have, say, a 25 ohm output impedance, then you can start to understand where you might have a damping factor of 2 where their curve looks like this, and then a damping factor of closer to 8 where their curve looks like this. and that will create that boomy, bloated bass. An easy example to hear this, if you have access to it, is to take like something with really low impedance, like a Focal headphone, or one of the Fostex Biodynamics, like something from the TH or TRXOO line, or a TH900 or an Emutique, and plug it into an OTL tube amp like the Dark Voice or the Bottlehead Crack, or just even find a receiver, a surround receiver, if you will, play music through it, and just plug right into the headphone output on the front of it. And you can hear this bloated, sloppy bass because the damping factor is small here, and just less driver control. Okay, now a quick note here. Planar magnetic headphones are not as affected by this. Now I say not as affected. They will sound overall less quick, less controlled. They'll sound like a little bit more blended together, if you will, if you have a low damping factor with a planar headphone. But their impedance is nearly flat. Like they typically have a set value. A lot of them are close to 50 ohms, and their impedance curve throughout the entire frequency is nearly horizontal. Okay, almost a flat line there, which means they don't have those alternating high and low damping factors throughout the frequency spectrum. It's the same everywhere, so you get the same effect everywhere, which makes it less noticeable overall because you don't have these alternating sloppy loose control, tight control kinds of things going on like you do with a dynamic driver. Okay, I think we can wrap this up now. I hope this clears up some things. Remember, the output impedance is the internal resistance at the output of an amplifier, and typically lower is better unless you know you're going to match a high output impedance with a high impedance headphone like a Sennheiser HD650 to an OTL tube amp like the Bottlehead Crack. Okay, but outside of situations like that one, lower output impedance, the better. The damping factor is the ratio of load impedance to source impedance, okay? The impedance of your driver divided by your output impedance. And what that damping factor tells you is the amount of control the amplifier has over the driver, and specifically its ability to stop the driver from moving once it's already moving. All right, and then headphone and speaker drivers and the output impedance, they share the amount of amplifier energy that's available at any given instant in time. So the more energy that the output impedance takes out and converts to thermal energy, the less energy goes to the headphone or the speaker driver to control its driver motion. Okay, and that can have an audible effect. Right, and this is why generally lower output impedance means damping factor and a more controlled sound and is thus desirable. Okay, thanks for listening. I am WaveTheory. I hope that explains output impedance and damping factor and why they are important in audio. So again, if you liked what you saw here, please like, subscribe, hit the bell, all of those things for this new channel, and be on the lookout for both equipment reviews and more teaching videos like this going forward. All right, have a great day, everyone. Enjoy the music.